to Raw Perfect classes. In this video, I will discuss operating systems topic, that is deadlock, which is most important for BSIT, BCA, MCA, MTECH, BTECH, UGC NET, GATE exams or any type of competitive exams which are related to computer science and computer applications. This topic is most important. Now, I am going to discuss about deadlock. When create deadlock in operating system? Deadlock is that situation. Deadlock is that situation where execution of two or more processes is blocked. Execution of two or more processes is blocked because each process holds resources and wait for other resources which are held by some other process. For example, these are two resource 1, this is resource 2, and here process 1 and process 2. Here process 1 holds the resource 1 and process 2 wait for resource 1. Process 1. On the other side, process 1 wait for resource 2, but this resource is held by process 2. Process 2 holds resource 2. Process 1 P1, that is process 1 who holds resource 1. Process 2 here demands and waits for resource 1. On the other side, process 1 demands and wait for resource 2. None of two processes can complete and release their resource. So thus, both processes keep waiting infinitely. So this type of situation, this type of condition is created deadlock in operating system. Now there are some conditions for deadlock. Conditions for deadlock. There are four necessary conditions for the happenings of deadlock. First is mutual exclusion. Second is hold and wait. Third is no preemptions. Fourth condition is circular wait. In mutual exclusion, by this condition we can say that there must exist at least one resource in the system. There must exist at least one resource in the system which can be used by only one process at a time. If there exists no such resource, then deadlock will never occur. For example, we have given a printer. We have one printer, a resource that can be used only by one process at a time. If another process wants to use this printer, then it creates the deadlock because process 1 hold it and set to process 2 to wait. If process 1 not release it, then process 2 will be waiting list. So that's why that create the condition of deadlock, and this type of condition is called mutual exclusion because we have only one resource and one process. One process can use only one resource. Another process cannot use it at a time. That is a condition of mutual exclusion. And second type condition is when there are two processes. There are two processes and two resources. For example, we have one printer and another is a scanner. We have given another is a scanner. P1 use printer. Use the printer, and P2 use scanner. After some time, he said he wants to use printer. And P1 said he wants to use scanner. But both are not release their resources, printer and scanner. Then that condition is deadlock condition because both are hold and wait. Both are said to each other hold and wait. There must exist a process which holds some resource and waits for another resource held by some other process. This is called hold and wait. Now third condition is no preemption. No preemption means once resource has been allocated to process, when printer is given to process 1, it cannot be preempted. It means resource cannot be snatched forcefully. P2 cannot be snatched this printer from P1 forcefully and given to other process. Process must release the resource voluntarily by itself. If P2 try to forcefully take that printer, that is called preemption. So there is a condition no preemption. That means P2 cannot take the forcefully printer from P1. So that is condition is no preemption, and this condition creates the deadlock. Fourth is circular wait. Circular wait. All the processes must wait for the resource in a cyclic manner, where the last process waits for the resource held by first process. For example, here we have this P1, here P2, resource 1, resource 2, and here P3, here resource 3. P1 holds R1 and wait for R2. R2 holds P3 or R3 resource and wait for R2 resource. P3 holds R2 and wait for R1 resource, and P1 also wait for R3 resource, and P2 also wait for R1 resource. That means all processes hold one resource and waits for another resources in a circular form. That is known as circular wait. So here we can say that all four conditions must hold simultaneously for the occurrence of deadlock. If any of these conditions fail, then system can be ensured deadlock free. All these four conditions should be hold simultaneously for the occurrence of deadlock. If any one condition fails, then we can say that system can be ensured deadlock free. Now I am going to discuss how to handle deadlock. If they create a deadlock condition, then what strategy we will be used for handling that deadlock in operating system. Strategies for handling of deadlock in operating system. If deadlock creates in operating system, then what strategy we will be used for solving, for handling deadlock in operating system? There are four types of strategies. Four types of strategies. First strategy is you can avoid deadlock avoidance. You can avoid the deadlock. Second, deadlock prevention. You can, if deadlock creates, you can prevent it. Third, deadlock detection and recovery. Fourth is deadlock ignorance. You can ignore deadlock. Now first is deadlock. First will be deadlock avoidance. In case deadlock avoidance, in case deadlock avoidance, we can say that this strategy involves to maintain a set of data, using which a decision is made whether to entertain the newest request or not. You want to entertain new request or not. If you want to entertaining the new request causes the system to move in an unsafe state. If you want to entertain the new request, that means you can move your system in a unsafe state. Then it is discarded. This strategy requires that every process declare its maximum requirement of each resource type in the starting. if you want to deadlock avoid, then you have to must know what are the maximum requirement of each resource type in the starting of a process. The main challenge with this type of approach is to predict the requirements of processes before the executions. You have to predict before the execution what are the requirements of processes so that you can avoid the deadlock. For this, we use Banker's algorithm. In case deadlock avoidance, we use Banker's algorithm. Banker's algorithm is the most important example of deadlock avoidance strategy. Now next type is deadlock prevention. Banker's algorithm, how to solve this problem, I will discuss in next videos in detail. Now I am going to discuss about second point, that is deadlock prevention. This strategy involves designing a system which violates one of the four necessary conditions, which are required for the happenings of the deadlock, and this ensure that system remains free from deadlock. That means those four conditions which are discussed in previous videos, previous slides, that should be violated. Out of four conditions, one condition should be violated so that system will remain free from deadlock. First condition, that is mutual exclusion. Second, hold and wait. Third, no preemption. Fourth, circular wait. In mutual exclusion, to violate this condition, all the system resources must be such that they can be used in a shareable mode. Means there should be such type of resource which can be easily shareable by all other processes. In a system, there are always some resources which are mutually exclusive by nature. So this condition cannot be violated. Hold and wait. This condition can be violated in these ways. According to first approach, you can say a process has to first request for all the resources and it requires for execution. Once it has acquired all the resources, only then it can start its executions. And this approach ensures that process does not hold some other resources and wait for other resources. But its drawback is that it is less efficient, it's not implementable, and it's not possible to predict in advance which resources should be required for the during execution. And according to second approach, we can say a process is allowed to acquire the resources it desires at the current moment. After acquiring all resources, it starts its execution. Now, before making any type of new request, it has to compulsory to release all the resources that it holds currently. So this approach is efficient and implementable. According to third approach, we can say that a timer is set after the process acquires any resource. After the timer expires, a process has to compulsory to release all type of resources which he has hold. And third condition, that is no preemption. This condition can be violated by the forceful preemption. A process is holding some resources and requests other resources that cannot be immediately allocated to it. that cannot be immediately allocated to it. Then, by forcefully preempting the currently held resources, and condition can be violated. Means P1 hold resource P2 and P2 holds resource resource 1. Then P1 forcefully set to P2 to release the resource resource 1, and P2 can be set to P1 to release the resource 2 so that they can use it. But this method is a preemption method. In this method, they violated the condition of no preemption. When this condition is violated, then there is no deadlock. You can prevent deadlock. A process which is allowed to forcefully preempt the resources which are forced by some other process only if it is a high priority process or a system process. The victim process is in the waiting state. Now next is a circular wait. This condition can be violated by not only allowing the processes to wait the resources in a cyclic manner. To violate this condition, there are some approaches that should be followed. According to first approach, you can say that a natural number which is assigned to every resource, and each process is allowed to request for the resources either in only increasing or only decreasing order of the resource number. In case increasing order is followed, then a process requires a lesser number resource. Then it must release all the resources having larger number, and vice versa. And this approach is most practical approach, and it must be implementable. And this approach may cause starvation but will never lead to deadlock. So we can say that deadlock prevention strategy can be implemented when we violates any one of condition which are necessary for the happening of deadlock, that is mutual exclusion, hold and wait, no preemption, and circular wait. Out of these, any one condition is violated, then we can say that deadlock is prevent, because system is deadlock free. Now next is a deadlock detection and recovery. This strategy is used for handling of deadlock in operating system when we can say that this strategy involves waiting until a deadlock occurs. After deadlock occurs, the system state is recovered. The main challenge with this approach is to detect that deadlock. If deadlock is created, then it should be detect and recover. And in deadlock ignorance, this strategy involves ignoring the concept of deadlock and assume that it does not exist. And this type of strategy helps to avoid the extra overhead of handling the deadlock. Windows, Linux use this type of strategy. Windows, Linux use this type of strategy and is mostly widely used method, and it is also called ostrich approach. This type of approach is called ostrich approach. Now I am going to discuss its practical questions related to deadlock. First question is, a system. A system is having 3 user processes and each requiring 2 units of resource R. The minimum number of units of R such that no deadlock will occur. We have to find out minimum number of units of resource R such that no deadlock will occur. For calculating it, solution of this question is the number of units that each process holds, that is equal to less than maximum demand. One less than its maximum demand. You can say there are 3 processes. Processes is 3 and each process required 2. That means 3 into 2, that is 6, and less 1, 5. But how to calculate it? There are P1, P2, P3. P1, P2, P3. Each required 2 resources. These are total 6. The number of units that each process hold 1 less than its maximum demand. That means 1 minus 5. But minimum number of units of resource will be calculated by total resource. Each will be required 2, but they can hold, each can be hold 1 resource. If ensure they deadlock, then they can hold 3 resources, but we add 1 source with that is total 4, and this shows that minimum number of units of resource are that ensure no deadlock. 3 plus 1, that is 4. 4 minimum number of units of R is required for 3 resources, because when P1 use 2 resources, R1, R2, P2, P3, they have R3, they have R4. When P1 use R1, R2, after releasing these 2 resources, out of these 1 resource can be used by this one and 1 resource used by this one. So that's why you can say total resources will be required total 4. Second question, a system is having 10 user processes. 10 user processes, each require 3 units of resource. Minimum number of units of are such that no deadlock will occur. So you can find it. Maximum number of units of resource that ensures deadlock, that is 10 processes multiply 2, that is 20, and minimum number of units of resource that ensures no deadlock, that will be 20 plus 1, that is 21, because P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, total 10 processes. First use 3 resources and others have 2 resources. If they want to know deadlock, then when these first process complete his task, then it will release all these 3 resources. R1 goes for R2, R2 goes for R3, R3 goes for P4, and after they using all their work, after completing their work, they will release all these resources, and after these all these processes will be use them. And thus you can say that minimum number of units of resource that ensure no deadlock, that is 20 plus 1 is equal to 21, because number of units that each process holds 1 less than its maximum demand. This is the method to calculate in worst case. Now next question. Next question, you have 3 processes P1, P2, P3, and P1 use 2 resources, P2 use 3 resources, P3 use 4 resources. The minimum number of units of R that ensure no deadlock. First of all, you have to find worst case. In worst case, the number of units that each process holds, that will be maximum demand minus 1. So maximum demand, that is equal to 1 plus 2 plus 4. That means how to calculate? 2 minus 1 plus 3 minus 1 plus 4 minus 1. Maximum demand, or you can say number of units of resources ensure ensures deadlock. That is equal to 4 minus 3, 1, 3. 3 plus 5, 3, 2, 5, 5 plus 1, 6. And minimum number of units of resource that ensure no deadlock. That is 6 plus 1, 7. That is your answer. Question number 4. In this case, we have given 3 processes, P1, P2, P3. And P1 required units of resource 21, P2 31, P3 41. In worst case, number of units each holds, that will be 21 minus 1, 20, 31 minus 1, 30, 41 minus 1, 40, and total is 19. And this is the worst case when deadlock can be occur. The minimum number of resource units that ensures no deadlock, that will be equal to 90 plus 1, 91. Now next question. In this question, we have given 6 units of resource are in system. Resource is given 6 units. Each process in the system requires 2 units of resource. Each process requires 2 units of resource. We have to find out how many processes can be present at maximum so that no deadlock will occur. In this case, we have already given resources and each process requires units, and we have to find how many resources can be present at maximum so that no deadlock will occur. For finding this, first of all, you have to write that minimum number of processes that ensures deadlock, that will be equal to 6, that is given, and maximum number of processes that ensures no deadlock, that is equal to 6 minus 1, 5. 5 is that 5 means number of processes 5 that can be present at maximum so that no deadlock will be occur. In question 6, we have given resources 6 units minimum resources of units, that is given 6, and each process requires 3 unit of resource. Now we have to find processes. How many processes present at maximum so that deadlock will occur? This question is just like same previous question which I have discussed in previous slide. So first of all, minimum number of processes. Minimum number of processes that ensure deadlock, that will be equal to 3, and maximum number of processes that ensures no deadlock, that is equal to 3 minus 1, 2. Because total resources units are 6. 6 will be divided. Each requires 3. And 3 minus 1, 2. That means each have 2, 2, 2, 2. That means total processes will be P1, P2, P3. That's the minimum number of processes that ensure deadlock, that is 3. And maximum number of processes that ensure no deadlock, 3 minus 1, that is equal to 2. Now next question. In question number 7, we have given resources. Resources are, that is given 100 units. If we have given 100 units of resource are in the system, and each process in the system requires, each process in the system requires 2 units of resource, then we have to find out processes. How many processes can be present at maximum so that no deadlock will be occur. Same question. In this question, you can see there are 100 units. That means 1 unit if used by each process, that is 100 resources. You can say that minimum number of processes that ensures deadlock, that will be equal to 100, and maximum number of processes that ensures no deadlock, that will be equal to 100 minus 1, that is 99. In next question, in this question also given resources 100 units, and each process requires 4 units of resource, and we have to find out processes at maximum so that deadlock will not occur. 4 unit of total 100 units. Minimum number of processes that ensures deadlock, that will be equal to, you can take here 4 minus 1, that is 3, and when we divide 100 by 3, that is 33, and plus 1, that is 34. You can say 34, and maximum number of processes that ensures no deadlock, that is 34 minus 1, 33. In next question, in this question also we have given resources 100 units. Now each process 5 units of resources. We have to find out processes at maximum so that no deadlock can be occur. In this case question, first of all, minimum number of processes that ensures deadlock, that is 100 divided by 5. 100 divided by 5 minus 1, that is 100 divided by 4, 25. You can say minimum number of processes that ensures deadlock 25. Maximum number of processes that ensures no deadlock. You can calculate it. 25 minus 1, that is 24. Now in next question we have given a computer system which has six tape drives with n processes. Competing for them. Each process needs 3 tapes. Maximum value of n. We have to find out maximum value of n for which system is granted to be deadlock free. For solving this question, first of all we have to find minimum number of processes that ensures deadlock. 6 divided by 3 minus 1, 6 divided by 2 is equal to divided by 6 divided by 2, that is 3. Now maximum number of processes that ensures no deadlock. 3 minus 1, that is 2. In next question, consider a system having m resources of same type, and these resources are shared by three processes. We have given three processes. These are A, B, C, and which have peak demands 3, 4, 6. For what is the value of m, deadlock will not occur. For calculating this, first of all, you have to find out maximum number of units of resource R that ensures deadlock. That will be calculated by 3 minus 1 plus 4 minus 1 plus 6 minus 1 plus 2 plus 3 plus 5, that is 10. Now minimum number of units of resource are that ensures no deadlock. No deadlock. That will be calculated by 10 plus 1, that is 11. 11 is the number of units will ensure no deadlock. These are the questions related to calculation of maximum number of units of resource that ensure deadlock, minimum number of units of resource that ensures no deadlock, and minimum number of processes that ensure deadlock, and minimum number of processes that ensures no deadlock. And in next video I will discuss Banker's algorithm. Thank you. If you watch my video, if you like my video, please like and share my channel with your friends so that they can take benefit from these free classes which are most important for competitive exams, and these most important questions for your competitive exams. Thank you.